Well, hello and welcome to Monday Night Calculus. We are talking about accumulation this evening. I've got Tom, Dick, and Steve Kokoska on the line. Really excited to have folks joining from Texas and Alabama. Drop a note in the chat where you're watching from. And students, please, if you have joined, please post your questions about the document here that we have posted. If you have not yet downloaded the student file, it is available to you down there in the description. I think Steve and Tom did a really nice job putting together some really good questions for this evening. So without further ado, I will let, I guess, Tom take it away, and we'll begin accumulating some great ideas.
Great.
All right.
Okay.
Very
Ooh,
good.
from Belize even. We've got folks from Belize watching too.
Oh, wow. I've been there. It's a great place.
I have
Cool.
too. It's pretty cool. Well, warm. And
Okay.
Colorado. And Colorado.
All
Okay.
right. So just kind of foreshadow Steve's first problem that he's going to be analyzing is actually a problem that involves a piecewise defined function. And this function is going to actually be the derivative of a function we'll ask some questions about. And we just want to emphasize this has been a mainstay on the AP calculus exams for, I think, close to 20 years.
Yep.
And it's like, this is a good problem to pay a lot of attention to. It's really rich in terms of the number of questions you can ask about it. Most likely it will appear on the non-calculator part of the exam, and certainly Steve's analysis will show that. But for teachers, if you want to generate some graphs like these and get some practice with the questions, just want to show you how you can get these onto a display. And so I'm going to show that on the TI-84. And so I'm going to construct a piecewise defined function that will then become the subject of Steve's analysis, okay? So I'm going to go to the y equals menu, and to get a piecewise defined function, I'm going to go to the map menu, and I don't see anything down here, but let me just keep scrolling down until, see down there at B piecewise. I'm going to enter that. And the piecewise function I'm going to enter is actually going to have 4 different pieces to it. So I'm going to right arrow key to up that up to 4. Then I'll enter OK. And you can see we've got a little bit of a template here. Not all of it's showing, but these blanks that are in the dotted boxes, these are for the piecewise formulas. And then on the right side of that semicolon is the domain. What interval will that be valid for? So the function we're going to look at, it's going to have the formula x plus 5. And that's going to be good for the interval from -5. And now I need an inequality sign. So I'm going to go to, it's the second shift of the math menu. It's a test menu. And we'll go actually to, you can see there's the individual inequality signs. I'm going to go over to conditions, and these are nice for these compound inequalities. And so I'm going to go down to number 7. I'll just type in 7. And notice it's gone ahead and filled in. So I've got -5 less than or equal to x. And x is less than, this is where I can put in the other endpoint of the interval. And the other endpoint of this interval is going to be -3, okay? And now we'll just continue and do that for each part. The second part, I believe it's going to be -2 times the quantity x plus 2. And that interval that'll be good for will be from -3. Notice it's starting out from where the other interval left off. And then I'll go to that conditions menu on test. There we go. I'll do 7 again. And then the next endpoint I'll put in is -1. Okay. And bear with me, it won't take too long here. Okay, our next piece, very simple actually, it's just x minus 1. And that'll be good from -1. And again to the test conditions menu. From -1 less than or equal to x, and x is less than +1. And now the last piece, and this last piece, by the way, the graph that you see Steve display, there was only a formula given for this last piece. And so what I had to do is, these other pieces are linear. I had to look at just what the straight line pieces look like to figure out what the formula should be. But this one, we're actually given a formula for it, and it's 4 minus the quantity x minus 3, that quantity squared. And this final interval is from 1, and that's going to run from 1 up to, whoops, excuse me. Get over to the conditions menu. This is one where I'll actually use 5. So this will be inclusive on both ends. So 1 less than or equal to x, and x less than or equal to 5. I think that'll complete our formula. And now let's take a look at what the graph looks like. I think this one's actually going to look pretty good in a zoom decimal window. So I'm going to the zoom window, down to zoom decimal, and then let's take a look. And there we go. All right. So that's generating a graph. And again, this is going to be the graph of the derivative of another function. That will be the topic of discussion. And then Steve's going to ask us some questions about this. So I'm going to turn it back over to Steve at this point.
Okay.
And we'll go from there. All right. So I'll stop my share. Back to you, Steve.
Good. Thanks, Tom. Curtis and Tom, it's so wonderful to be back with you again on Monday night. I just wanted to remind people out there, teachers especially, that they can send you questions anytime at all, not just on Monday nights, about any specific calculus concept, idea, problem, and we'll be happy to answer them. We'll be happy to get to them. I know you'll forward those along to us.
Yes,
And also,
sure.
I'd also like to encourage teachers to ask their students to participate. I know we had a couple of teachers tell us they were giving extra credit to students who participated, but we really do enjoy having them here and having them interact with us too. That's a lot of fun.
Yeah, we really do. And I did, in fact, just get a question from a student. I was able to answer it here in the chat, but just so you guys are aware, we're talking about endpoints
Okay.
on the piecewise function there, whether or not the 84 actually puts an icon or an identifier on the screen of an open endpoint or something like that. And I suppose if you did trace and you used the trace key and you ended up on an not included or not defined endpoint, you know, when you hit a less than, so long as the function wasn't also defined elsewhere for that value of x, then it would just not return a y. But otherwise, there's no marking on the screen.
Yeah, there wouldn't be like an open circle like we use when we're drawing graphs. But
drawing by hand.
If you hit right on a place where it's undefined, there will be a gap in the graph.
Right, a hole, or yeah, you could potentially see a visible hole if it lands on a pixel.
But it won't be circled like an open
but it
circle.
would be a circle, right?
See in textbooks. So.
Right.
This is actually a very good question, Curtis, because this is one of the things I argued about briefly when I was on the development committee. For a graph like this, I argued that we ought to put solid dots at -5, 0, and 5, 0 to emphasize that, you know, indeed the graph does go through those 2 points. But
that's interesting. Instead of approaching those points.
Yeah, I mean, it's not crystal clear what's going on. Tom and I have talked about graphs and interpreting them before many times, and I always thought, well, you know what? You ought to make it clear to the kid, to the student who's ever reading the problem. But anyway, well, I'm not going to win that argument. So here we go. Here we go. This is, as Tom said, this is a typical problem that's been, problems like these have been asked on the exam for probably the last 20 years in a row. The analysis of a function. And recently they have been given graphically, we've been given a graph of f prime. I've circled a couple of things here. I've written something down here that I want to remember to talk about. We know that this function f is defined on this closed interval -5 to 5, and we know that f of 1 is equal to 3. We're going to need that later on in this problem, for other parts of this problem. So as Tom said, this graph consists of 3 line segments and part of the graph of a parabola. I've put over there on the right-hand side a Q circle. You know, many of these problems on the exam have consisted of straight line segments and quarter circles, maybe even a half circle. We did see one recently that had part of a parabola in it, but you know, I kind of feel like there'll be some straight line segments in another familiar sort of graph, like maybe a trig function in there, maybe part of an exponential function in there. So I think they're leaning slowly, moving slowly away from just straight line segments and quarter circles to including some other shapes. All right, so that's the graph of f prime, and we need to analyze that. We need to know for x between -5 and 5, and I've circled this. You'll notice that that's an open interval, but I'm going to come back and talk about that in a second and connect it with my question on the right-hand side in a minute. It says find all the values of x for which x has a relative minimum. Well, where does that occur? That happens when f prime changes from negative to positive, where the function is decreasing and then increasing. So what we have to do to solve this problem, to answer this problem, is to read that answer from the graph. And we see that at x equal to 1, f prime changes from negative to positive, and therefore there's a relative minimum. Now, these two statements right here would be sufficient for earning the point on a free response question. And in fact, you could probably combine these into one sentence. F prime changes from negative to positive at x equal 1, therefore there's a relative minimum there. All one sentence, fine. But you got to justify F prime changes from negative to positive there. Okay, what about my question over here? Now, I recognize that this is an open interval, but what if it were closed? We frequently get asked this question about this endpoint. Well, what about at x equal -5? I mean, if you think about starting at x equal -5, the function is now increasing as we move to the right because f prime is positive. It certainly seems like there's a relative minimum. But that's not true. And the reason is because you need to look at the definition of a relative minimum. And that definition says you must have an open interval about this value, x equals c or x equal a. And because of that, you cannot have a relative maximum or minimum at an endpoint of an interval. There could be an absolute max or min there, but not a relative min or a relative max. Common mistake. All right, well, what about B here? For x between -5 and 5, let's find all the values where f has a point of inflection. Well, all right, once again, we need to use the graph of f prime to determine this. And f would have a point of inflection wherever f prime changes from increasing to decreasing or the other way around. Now, I've probably written a little bit too much here, but there are indeed 3 points of inflection on this graph. They occur where x is equal to -3, -1, and 3. That's where f prime changes from increasing to decreasing or vice versa. I'm going to write a little bit more off to the side here, Curtis, because I think this is kind of a common mistake. Some students may answer this by trying to give ordered pairs. And so, for example, I'm going to write this, Curtis, but then I'm going to erase it. Some students will write -3, 2. They'll think, oh, well, there's a point of inflection at -3. And if you look at the graph, it goes through the point -3, 2. Well, that's wrong. Because -3, 2 is not on the graph of f. I mean, it could be, but we don't know that. So if a student were to write something like this and actually return ordered pairs for each of these, it's very unlikely they would get full credit. They might receive receive partial credit. But that's a common mistake. So students out there, as you're preparing for the exam, don't make that one. And down at the bottom here, part C, it says find all the intervals on which the graph of f is concave up and increasing, a very typical sort of a question from the exam. So the way that I tackle this is, where is f increasing? Well, that's where f prime is positive or 0 here. I can include the endpoints. We can argue about that on another Monday night calculus, or if people want to send us questions, we can. But we've talked about this frequently. F is increasing on those intervals, and I believe you can include the endpoints. And the reason for that is going back to definition. Where is f concave up? Well, it's concave up where f prime is increasing. Those are open intervals because of the definition of concavity. And then all I really need to do here is to look at the intersection of those intervals. And I think I've done that. And I've got 2 intervals here. Now, on the exam, writing out these 2 things, these 2 lines, is probably not necessary. But it would help, perhaps, in attaining some partial credit in the event that you made an error along the way. Good. I've got one more question, I think, here at part D, and this is a good one. It says, find the absolute minimum value of this function f over the closed interval -5 to 5. Well, let's see. If we're going to do that, we need to find the critical points of f, and we need to evaluate f at the critical points and at the endpoints. So where are the critical points? Well, those are the places where f prime is equal to 0, or where it doesn't exist. Well, where is it 0? Well, let's see. It crosses the x-axis at -2 and 1. Got those 2. I'm not going to put the endpoint here. Yes, sir?
We had a question come in, and I really like it.
Okay.
I started to answer confidently, and then I wondered.
Okay.
So the question is, when we are listing the values of x, where we might have a minimum, or where we're listing a set of values of x, can we say x equals and then do a list like you have here of -2, comma 1, comma whatever? Or do we need to list each x equals -2, x equals 1, x equals -4, whatever?
Excellent question. A list like this is sufficient.
Okay.
So on the previous.
Mark confirms that.
Oh, good. I'm
chat,
happy to hear that. Okay.
Good.
Very good. All right. So I'm not going to include 5 and -5 in this list because those are the endpoints. All right. And we'll be evaluating f at those endpoints. And are there any places where the first derivative does not exist? There are none. There is a desire, a tendency sometimes to say, well, wait a minute, there's a sharp corner here or an edge, and there's another one here, there's another one here. But remember, those would be places where the derivative of f prime does not exist. The value of f prime actually does exist at those places. So what I need to do is to evaluate f at 4 places. Let's see, the endpoints, -5 and 5. And these critical points are critical values, -2 and 1. Now, how am I going to evaluate f? Well, I'm going to sneak off to the side here and write a little bit more if I can. I'm going to remind you from the previous page, we know that f of 1 is equal to 3. And that's sort of a tip-off for me. I'm going to use that value in some way connected with the fundamental theorem of calculus. And this is the way that I think about it. I'm going to look at the definite integral from 1 to x of f of t dt, and that would be equal to f of x, I'm sorry, f prime of t, I apologize. That would be f of x minus f of 1. So that's just an application of the fundamental theorem of calculus, at least in my mind. I can solve for f of x here. I'm going to write one more step because I've got the room. So that's equal to f of 1 plus the integral from 1 to x, f prime of x, f prime of t, dt. I like to use a different variable in there. I think that's more proper or more appropriate. So some people look at this expression and think about this as a net change. We start at 1 f of 1, and we add to it the net change in f, and we come up with a new value here, f of x. So I'm going to use that equation here. I'm going to use the geometry in the graph. I might need to determine a definite integral here because I've got that parabola. Let's see what happens. So all right, what's f of minus 5? Well, f of minus 5 is f of 1 plus the integral from 1 to minus 5 f prime of x dx. I've used an x in there because there aren't any other x's and t's or anything in this expression. I'm going to use a property of definite integrals here. I'm going to reverse the bounds. And now in order to determine that definite integral, I'm going to use some geometry here. I have a triangle up here. It is above the x-axis. That contributes a positive value to this net area. I have another triangle below the x-axis that contributes area, but we're going to subtract that off because it's below the x-axis. And I think if I did all that correctly, I get a 3. These two values will cancel out. I think that's a 3. How about at minus 2? Let's see. That would be f of 1, definite integral from 1 to minus 2 of f prime of x dx. I'm going to use a property of definite integrals once again. There's that minus sign. But I need another minus sign in here when I use the geometry because that region is below the x-axis, minus 2 to 1. So I think those minus signs together give me a positive, and I think that value is 6. How about that? F of 1 is really easy to compute. I'm going to arrow down just a little bit if I can here, Curtis. F of 1 is pretty easy to compute because we have an integral from 1 to 1. That's just 0, so that's 3. And now, how do we get f of 5? Well, that's f of 1 plus the definite integral from 1 to 5, f prime of x dx. Well, over that interval, f prime is that parabola. There we go. Have I got enough parentheses in there? I think so. Now, I skipped a little step in here, Curtis. I apologize. This is a nice, easy integration by inspection. That's just 4x. But how do you integrate that? One way to integrate that expression, if you really wanted to, is to simply multiply out that binomial and maybe even collect some terms and integrate the whole thing, the whole integrand, term by term. But another thing you could do here, I know we have some really good students who watch, is that's just an integration by substitution with u equal to x minus 3. du is dx. We don't need any sort of quote unquote integrating factor in there. So I've kind of skipped that step, and I can see that. I know your good students are very good at this. That's just an x minus 3 cubed divided by 3. Okay, in the interest of saving a little bit of time, I plugged in the upper bound, plugged in the lower bound, did a little bit of subtraction, a little bit of collecting of terms. I got a 41/3. Tom and I kid about this a lot. I don't know why in these area problems, I don't know why in these volume problems, but there is frequently a multiple of 32/3. I don't know why that is. If I had to guess at an answer, that's always my guess, okay? So I need to look at this table and I need to pick out the absolute minimum value. And in fact, in this particular problem, it occurs at 2 places, at the endpoint minus 5 and at x equal to 1. So the absolute minimum value here is 3. A common mistake here that some students make is you have to be careful in reading the problem. This actually asks for the absolute minimum value. And so if a student were to do all this work and say, oh, the absolute minimum value is x equal 1, well, that's not quite right. If they say the absolute minimum value occurs at x equal 1, okay, that's correct, but it doesn't answer the problem, and so they would not receive full credit. So some things are as simple as, well, make sure that you answer the problem, make sure you respond with an answer that they're asking for. Tom, a little bit more technology here?
Sure. Sounds
Okay,
good.
here we go.
Okay. So Steve took us through an analysis of this problem, and it's very much the kinds of questions you could expect on the AP exam. Something you wouldn't necessarily see would be something about what the actual graph of F would look like. And that's because the graph of F prime was just presented graphically. There was a piece of it presented analytically. But here on the 84, we did take the time to get an explicit piecewise formula for Y1, which is our F prime. And we can use that fundamental theorem, like Steve said, to actually get an explicit expression. It's going to be a definite integral function for F. And I'm going to put that in Y2. So as Steve mentioned, it's going to have the initial value that we're given, F of 1, which is 3. And then we're going to put in the integral piece. And for that, I'll go to the math menu. And down there at number 9 is integral. And we get this nice integral template. And the integral was from 1 up to x. And I don't have to type all this in again. I've got it stored there in Y1. So I can go to my Y variables function. There's Y1. And this isn't particularly great form, but the variable of integration is really a dummy variable. The calculator won't get confused. The actual function argument is this upper limit x, but I can actually do a double duty with my x there. And now we could...
Tom, if you wanted to, Tom, can you actually put in another variable? Like, could you say if you wanted to y1 of t dt?
I believe so. I believe so.
Okay. Okay.
So yeah, if you really wanted to have the nicer form where you're not doing double duty on that.
Gotcha. Gotcha.
Now I'm going to go ahead and graph this. So we get our original graph of F prime. And now we're going to see, we hope, the graph of F. Okay.
It's thinking. Here it comes.
Oh my gosh, this is slow.
Yeah, how come?
And that's why I wanted to do this. If you think about this, every single function value,
right,
is having to compute this complicated definite integral that involves this piecewise function that's 4 pieces.
Yep.
That's just a lot of work. And so we may need to go down to the grocery store, buy some groceries, come back. But we could speed this up. So I'm going to bail on this for a couple of reasons. It's going too slow is the big reason. The other reason, though, I'm just hitting the on button to suspend this, is I can see, and taking a hint from Steve's table, I think these values are going to get off the screen here pretty quickly. So I'm going to do a couple of things in the window. The first one is just I'm going to increase my Y max to, why don't I make that 14.1? So I'll just add 10 to it. Okay, so that should give us enough vertical room. But
okay.
If we want to speed up how fast it actually graphs, the key to that is this thing down here that says XRes. And this will control how fast it graphs. Now, it will be a rougher looking graph, but you can really crank up the speed quite a bit. So, for example, if I make XRes equal to 4, it's going to graph 4 times as fast, literally, because it's only doing every 4th pixel. It'll still connect them up, give us a curve. That's a way to at least get a semblance of the graph more quickly. Like say, there is a sacrifice of how smooth it will look. But let's give this a shot and see what happens. So there's our derivative graph. You can see with the Y scaling different, a little bit of a change. And hopefully we'll see the graph of F come up a little bit more quickly.
Hey, there you go. That's pretty good.
There, yeah, we're making some progress on this. Yeah, it's still kind of slow. I mean, it's remarkable. We're really making this do a lot of work. And wow, so it's not a bad graph. And some of the things we can see is the absolute minimum
Yep.
It was at that left endpoint at -5 and at 1. It's like Steve analyzed. You can also see kind of where some inflection points were.
Uh-huh.
And then if you cared, the absolute maximum looks like it occurs. I'm not sure that was asked, but at the right endpoint.
Yes.
Way up there. But there's a way we can kind of check. Also, if you went to quit, you could evaluate your function f at any place that you wanted to. So, for example, I'll just pull up y bars y2. And if I wanted to evaluate that at, say, 4, it calculates it out. And what it's literally doing is the 3 plus that definite interval.
Hey,
Yes.
Tom.
Yeah.
Just a couple of notes. One, I know we've shown people this before, but can you hit the alpha trace button just so that folks realize they can also pull those variable names right off of there, rather than have to go through the menus to select it off of the menu key. Hitting alpha and trace, that F4 button is a nice shortcut to pulling in the y variables.
Yeah.
And utilizing those as functions.
I tend to forget these shortcuts, but this is one that's really worth, I think.
Oh yeah, that one.
Read that enough. Yeah.
That one is a big one. That one in the fraction input, alpha xt theta n, which it's not on your emulator looking there, but if you just hit the alpha and the xt theta n button, you'll insert a template for a fraction.
Oh, okay, that's a nice one to know.
Which is a nice one. It's printed on the calculator, but I know there were some that were printed before that operating system went out, and so sometimes it's not there. So the other thing that I wanted to make note of, there was a question that came in from a student that says it seems there's no problem using the same variable as an integration variable and the upper limit of integration when you're inputting this into the y equals, I think is the context of the question. And that's true, right, Tom? When you go to y equals and you're dropping in, there really is no issue with utilizing x in both of those locations. In fact, you kind of have to, right?
Well, I think you can use
that's
you use, actually Steve's
like a t or something else.
Yeah, you could, but you'd want to use, I think you would then have to say y1 of t explicitly.
Right.
Actually, maybe we should give it a try and just see what happens. Sure. I'm going to edit my y2 here.
And make that a y1 of t.
Of t,
and
yeah.
dt.
And see
and that may actually help.
And that is really better form. There we go. So we have a y1 of t, and then we're going to make the variable of integration t.
And I think you're right, Tom. I think that'll work.
I think. Now, we may get an error message, but let's give it a shot, see what happens. And we won't wait for the whole graph as long as it starts graphing.
Well, as soon as you hit enter, I think it should have, yeah. So you.
Yeah, it was fine. Yeah, that was good. Yeah, and that's a little bit better form, and I like that idea.
Yeah, that was a good question. Thank you.
Go ahead.
In the chat for that. Yeah, thanks a lot.
Okay. And if there's not anything else on that one, I'll turn it back over to Steve so he can dive on in.
Okay, very good. Steve. Cool. All right, I've got a couple of other questions here, Curtis, a couple of them that deal with technology. Tom does a great job with the TI-84 and the Nspire, but as you know, I enjoy using the Nspire. So I'm going to show you a couple of calculator screens and kind of explain a little bit about what I did here to get those. This question involves diners and coffee. This is from my brother-in-law who really enjoys both, seems to know every diner in the entire state of New Jersey. So let's suppose that a diner brews coffee, and the rate at which they brew coffee is modeled by this function capital R. And we know that it's ounces per hour and T is measured in hours. And coffee is consumed by our customers at this rate, this function D. And there are 500 ounces of coffee ready for sale when the diner opens. That's coffee from yesterday, but they kept it in the giant urn for ready for the morning. Okay. So the first question is, how much coffee is brewed by the diner during the 12-hour period 0 to 12? Well, okay. Very typical sort of a question again on a free response question on the exam. We have a sort of a rate in and a rate out. And to answer this question and get full credit, students would only have to do the following. Write the mathematical expression that they are going to evaluate. It is a definite integral from 0 to 12 of R of T dt. I would like to suggest that you do not write the explicit function R in there, because if you do, there is a chance of making a copy error, in which case you would not receive full credit, even if the correct answer appears. So if there is a named function given to you, you can use that named function. And in fact, you can even create your own function and give it a name, like F or G or Q, and use that. So this is perhaps the most succinct way to get full credit for this problem. And I'll show you how I did this on my calculator in a second. I've written the mathematical expression. I went to my calculator and typed that in and got an answer. And there's the numerical answer, correct, I believe, to 3 decimal places, 3 places to the right of the decimal. Rounded or truncated, I tend to round. B, is the amount of coffee in the diner increasing or decreasing at T equals 4 hours? Well, let's see. In order to answer that question, I've got to take a look at and compare the rate in and the rate out. So I'm going to look at this difference, R of 4 minus D of 4. What's the instantaneous rate difference, R of 4 minus D of 4? Well, once again, I did this on my calculator. I showed the mathematical setup. If you were doing this on the exam, the truth is that you don't have to report a value here. If you do report a value, it must be correct to the number of digits reported up to 3 to the right of the decimal. So a test taking is, in this case, since the value is not asked for, it would be smarter to just say, well, that's less than 0. Because it's less than 0, that means D of 4 is greater than R of 4. So the amount of coffee in the diner is actually decreasing at that time, at that instant, T equals 4 hours. Cool. All right, we'll get to the technology here in a minute. Let's look at C. Let me show you what I did with that one. We've seen a lot of problems like part C recently, and I actually solved these a little bit differently than what you might see on the scoring guidelines. I tend to solve these a little bit more explicitly. So this is asking at what time is the amount of coffee in the diner a maximum? I need to know this because I have to make sure that I have a big enough urn to hold all this coffee. So I think about a function, first of all, that represents the total amount of coffee in the diner at time t. So that, in this case, would be 500, the initial amount, plus the definite integral from 0 to t of the difference, rate in minus rate out. So I've kind of used the x's and t's in a little bit different way here, but you'll notice that I did indeed use 2 different variables. T is sort of the variable that goes with my function a. X in this case is sort of the dummy variable that goes with this integrand. Well, if I want to maximize this function, I need to find the critical values, and I need to evaluate the function at the critical values and the endpoints. Okay, what are the critical values? Well, I need to find the derivative of this function. And the derivative of that function, first of all, the derivative of 500 is 0 with respect to t. And the derivative of that integral part is just the fundamental theorem of calculus. So that's just R of t minus d of t. So what I need to do is I need to take this expression, I need to set it equal to 0 and solve, and I did that. So I'll show you how I did that on my calculator in a moment, but there are 3 values where that occurs, where a prime is equal to 0. There are the values. I don't know why I reported those to a little bit more accuracy, but 3 digits is all that's necessary. But remember, store these values in your calculator to the greatest degree of accuracy allowed. Don't just visually round or truncate. And now here's my candidates test. I know that A of 0 is 500. That's how much coffee was in the urn to begin with when the diner opened. And I evaluated this function A using my calculator at these 3 values, little a, b, and c, and to 12. And it looks like the maximum amount of coffee in the urn is around 2,145 ounces of coffee. Man, that sounds like a lot. And that occurs at time t equal to 3.053 hours. That's a neat problem. Let me show you a little bit with technology on the TI-Nspire, and we'll see if Tom wants to do anything on the 84 or not. I really do enjoy the TI-Nspire, and I use a CAS version. I really appreciate the computer algebra system in here, which at least I think for Tom and I, Curtis, is still an absolutely remarkable thing that the calculator can actually solve these problems symbolically. So I defined my functions. Here's R and here's D. And over here on the right-hand side, here's a calculator screen that shows this calculation, that definite integral from 0 to 12 of R of t dt. There's my 9747.039. Here's the answer to part B, or the calculation that I need in part B, R of 4 minus D of 4. That's pretty easy. And now I need to find these places where that first derivative is equal to 0. So let's see, this is kind of cool. Now, there are a couple of ways to do this. One of the ways that I like to do this is by using the built-in zeros command. And the reason that I like that is because it puts the answers in a list that I can refer to so that I can grab specific elements of that list. Now, I've learned that there is a command built into the TI-Nspire which allows you to convert answers to a list, and that's fine. That will work with a built-in function like solve. But this is also very convenient. So what I'm doing is I'm asking the calculator to find the zeros of that expression. It's kind of hard to see, but there's a vertical bar in there, which in my mind stands for such that t is between 0 and 12. And this over here says store all of those values in a list that I'll call Z, and there they are. So I can now refer to each one of those values, for example, as Z sub 1, Z sub 2, and Z sub 3. I can then store those in specific variables if I wanted, like little a, little b, and c. I think that's a nice feature. Now, one more thing that I did here to get to my answer, to get to my candidates test, is I defined this function A, which represents the total amount of coffee in the urn, at any time t. And then over here on the right-hand side, Curtis, I went to a lists and spreadsheet page. So without showing you all of the calculations, what I do find really cool here is that I can actually create this table for the candidates test in a lists and spreadsheet page. So you can see my values of t in that first column, and I evaluated this function A in the right-hand or in the second column. I can now look at that and pick off the maximum value, and that occurs at time t equal 3.053. Very cool. Not content with all of that, I wanted to see what this would look like graphically. And so On the bottom left-hand side over here, this is a graph page. And I actually sketched the graph of A of t between 0 and 12. And I used a built-in function here to find a maximum between 2 points. And I feel pretty comfortable about this. There's my maximum value occurring at 3.05 roughly. There's my maximum amount of coffee in the urn. I think I've put all of this together analytically. I've got the mathematical expressions. I've got the technology to back it up. I feel pretty good about this answer. Cool. Curtis, any questions about that one?
I've not gotten any questions on that one, no.
Okay. Tom, should I do 3 or would you like to do
Yeah,
it?
go ahead to number 3, Steve, and then
Okay.
I'll show some more things on the 84 then. Okay?
Okay, very cool. All right. So this one has to do with the Louvre Museum in Paris. It is one of the most popular, the world's most popular museum, I believe. And this is another rate in, rate out function. I'm going to show you some of my answers that I got with technology, but I guess Tom will show you how to get some of these with the 84. So the rate at which people enter this museum is given by this function, capital E. The rate at which they leave is given by capital L. These functions, I'm sorry about this, but they're also valid from 0 to 12. Those are this museum is open for 12 hours, let's assume. And at t equals 0, when the doors open, there are no people in the museum. Find the total number of people who have entered the museum by 1 o'clock. Well, 1 o'clock corresponds to t equal 4. So again, all I need is the mathematical expression. I go to my calculator. That's what I got. Tom's going to back me up on this, I hope, with the 84 in a little bit. Often in these questions on the exam, students are asked to round. And you would kind of do that naturally because this is a question about people. We don't often take off for this, but I would encourage you, it depends on who the chief reader is. I would encourage you to read the problem carefully. And if it does say, people or fish or penguins or whatever they are, round to the nearest whole number. So this answer, I believe, is 4003. Are the number of people in the museum increasing or decreasing at 1 o'clock? Well, again, I've got to take a look at the difference in rates here, E of 4 minus L of 4. I think that comes out to be a positive 406. So that tells me at this time, the number of people in the museum is increasing. Let's see if we can find this function n of 8 and explain the meaning. Well, if I evaluate n of 8 using my calculator, I got 2406. And because that is a difference in rates, an integral of a difference in rates, that tells me that there are approximately 2,407 people in the museum at that time. And finally, find the maximum number of people in the museum. Well, okay. It turns out for this problem that there is only one critical value. That is where E of t is equal to L of t, or E of t minus L of t is equal to 0. That occurs around 5.79 hours. There's my table of values. And the maximum number of people in the museum is approximately 27, 28. Notice I rounded a little bit there. One word about this before I hand it over to Tom Curtis. There's only one critical value in this interval 0 to 12. And so there is an argument that can be made here that says, well, there's only one critical value. And if I know that the function is increasing and then decreasing, I know that's got to be where the maximum is. Yes, there is an argument there, but we're often hard-pressed to find a student response that makes that argument correctly and completely. So I have always found, and I always advocate, that a table of values is the best way, the most efficient way to answer these types of problems. Cool. Yeah. Tom, little TI-Nspire technology?
Sounds good. Yeah, okay. Let's give it a shot.
Cool.
Okay. So on this problem, I've gone ahead and taken the liberty of going ahead and entering into Y1 and Y2 the functions for E of t and L of t. So this first function, and you'll notice I've replaced the, I'm going to use x for time because we are in the function grapher. Okay. So the rate at which folks are entering the museum is given by y1, 500 times natural log of x squared plus x plus 2, where x is measured in hours. And then y2 is the rate at which they're leaving. And that's involving this inverse tangent function. So let's actually take a look at these graphs, see what they look like. Now, we're given an interval for these. So I'm going to go to my window and go ahead and change my x min and x max to 0 to 12. That was the relevant time period. And let's just dive in and graph. I'm not seeing much. Oh, there we go. There's something there. But yeah, if we think about it, given those coefficients, this is way. So, I could take some time and try some value, figure out what would be a good Y range to use. But there's a nice zoom feature that you can use. You go to the zoom menu. It's actually not on the first page, but if you scroll down past zoom stat, it's this one, zoom fit. And what zoom fit does is it leaves your x min, x max, whatever they are, leaves that alone, but then it samples those x values and figures out a good range for you, something that's going to include your minimum and maximum values for your function, or in this case, two functions. So let's go ahead and try that and see what happens. Very nice. And notice that it's just the right height to include the minimum and maximum value. It looks like that red function is the one that has the broader range of values there. And it's hard to tell what the scaling is on Y, but of course we could just trace and we get some sense of scaling here. So let's see, this blue function is our rate at which they're entering.
Yep.
Remember that, I see the formula up here, that's matching our E. I can switch with the up or down arrow to the rate at which they're leaving. And looking at these two graphs, I can see that the rate at which they're entering is greater than the rate they're leaving up until this value here where it crosses. And then after that point, they're leaving faster than they're entering. So this is going to be where that maximum value is going to be. It looks like it's a little bit less than 6. That might sound a little familiar. But another way to get at that value is we could go to the calc menu and let's get an intersect, 5. And the first curve, well, there's only 2 here, so that's easy enough. Second curve's the red one. And then we want to move kind of close to where they cross. Okay, and then when we hit enter, it's giving us that more precise value. And I think, let's see, did you actually find that? Yes, you did, Steve. And that's looking really, really good.
Yep.
And this is actually giving not the value of the maximum. Notice this Y value here is that's actually the rate at which they're leaving at that time, which we know will be the same as the rate at which they're entering. So to actually compute that, what I could do is go back to the calculator menu. If I pull up X, it is that intersection value. This is the value that Steve called A. So let's go ahead and store that in A. And then if we wanted to actually find that maximum value, we'd want to do an integral. And this would be the integral from 0 to A. This is really nice, not having to copy this those values down, and it keeps them up to the maximum precision that's available to the calculator. And then the function, I think, is actually going to be the y1 minus y2, the rate that they're entering minus the rate that they're leaving. That's what we're going to integrate. Now I want to use that shortcut that Curtis was talking about. That was the alpha xt theta. Oops.
Alpha F4.
You're looking for the variables?
Yeah.
Yeah. Alpha and F4.
Oh, alpha F4. Yeah. This was for the fraction template. Yeah. There we go. So I think the rate at which they're entering is y1.
Oh, and Mark Crawley just made a nice point too, that if you wanted to store the y coordinate that you had gotten earlier, you can also do that very quickly by storing alpha y.
Yeah.
Oh, very nice. Yeah, yeah. If we needed that value for something, what was the rate, the common rate between those? Yeah, nice point. Thing is, you need to do that kind of right as soon as you get back from the graphic screen before you use X for something else, right? So.
Right.
Okay.
Or if you graph something else, or if you go back to, if you do anything else that's going to impact that variable X, the variable does change.
That's looking good. There's that 27.78. One if we round to that third decimal place. So great. Okay. All right. So
Tom, before you leave this, would you just go back to the graph screen just for 1 second?
Sure.
There's just one thing that occurred on the screen that is simple, I think, but we haven't talked about this in a while. If you take a look at the vertical axis,
yes,
it looks awfully thick.
Mm-hmm.
And could you just explain to us why that is, why that has occurred?
Well, let's take a look at the window. And with this,
it's down on Y.
Yeah, Y scale.
Yeah.
This is where it's putting the hash mark or the tick marks on the Y axis. And if we think about, notice here we can actually see what the Y scale, we didn't figure this out. It figured it out for us. It said, okay, this would be a good Y scale to get both of these graphs nicely on the screen. And it did a nice job. But if it's going from 0 to 2,797 and it's putting a tick mark every unit, man, that's just going to be solid tick marks on the.
That's what's happened. Yeah.
Yeah. So we could change that Y scale to something like, say, 500.
Okay.
Now it's going to put a tick mark every 500 units. And if we go back to the graph, there we go. Same graph. Nice. But now I know that these are actually worth 500 apiece.
Yep.
It's going 500, 1,000, 1,500, and so on. So that's nice. Yeah.
Very cool.
And of course, as soon as we start tracing, we're seeing kind of what kind of Y values we're dealing with. Okay.
Okay. Cool.
I'll stop there and turn it over to you. I think we're probably getting close to running out of time there.
Yeah, Curtis, we're just about out of time. Let me just mention a couple of other problems here. Number 4 is also about accumulation. This has to do with Vermont maple syrup. Tom and I lived in New England for quite a while and really enjoyed our pancakes with real maple syrup. So this is a nice problem about collecting maple syrup. There's some technology in there. There's a question about estimation using Riemann sums. And there's an overtime problem here that has to do with Oreo cookies. It turns out that Oreo cookies are the biggest selling cookie in the history of the universe. I did not know this, but if you watched the Super Bowl yesterday, I believe there was a commercial involving Oreo cookies and spinning it off if the white cream goes to the left or the right. I did not know that, but this is very appropriate. So this is a nice question. And I wanted to end by just taking a look at this last one here. And I'll tell you why. It's not that this was a difficult definite integral, but this was a good question, one that I haven't seen in a while on the Facebook group. It was evaluate this definite integral. And actually, Mark Corrali and I have been talking about this issue recently. How do you evaluate this kind of a definite integral? Well, the first thing you have to do to find an antiderivative is you have to divide. I might call this long division, or I might call this writing this integrand as two separate fractions. Something that students might not think about, might be looking for something more complicated. Okay, I'm not going to go through this in gory detail. I write it as two separate fractions. I integrate term by term. One of them is a natural log. One of them is the power rule, backwards power rule. Pretty straightforward. And here's the symbolic answer that I get when I work this out by hand. I see this as a very typical sort of a multiple choice question. However, if students are using a CAS machine, they may want to check their answer. Now, this one's pretty elementary, but this is the reason I'm putting this in here. If you ask the TI-Nspire to find this, it gives you back just a little bit different looking symbolic answer. And you might think, oh, what's wrong here? Did I make a mistake? Not necessarily. It's just that the CAS system has returned an answer in a different form. It's pretty easy to think about what it's done here or why these two are equivalent by thinking about properties of logarithms. But the reason that I put this in here is because the CAS machine does not always return the answer that you are expecting if you work it out by hand. And I think you should be attuned to that, aware of that. Very cool, Curtis. I'll post these or send you these answers tomorrow morning. Great work.
Yeah, great work, Steve, Tom. It was another great session tonight. Teachers, I put a little link in the chat or a reminder in the chat. If you watched all the way through, please email me for the professional development hours. I'd be happy to send you a link to a certificate that you can generate. Also, we are going to be back on here in about 2 weeks, February 26th. We'll be chatting about, I don't remember what we're going to be chatting
Differential equations.
Differential equations in 2 weeks.
Fields.
We'll be looking at slope fields and
Yeah.
differential equations, all kinds of
stuff.
exciting things there. So be looking forward to that. And finally, yeah, we're going to be doing another pre-cal session here at the beginning of March. So if you've got students that are interested in that, be sure and point them to that. As always, invite your students to utilize these questions and these reviews as prepare for the exam or for your class. It'd be great. And we'll try our best to answer questions as they come up. All right. Thank you. Until next time, we'll see you in 2 weeks.